Let's review some of what we have learned about linear functions. In the beginning of the year, when we studied sequences, we learned that arithmetic sequences were linear and that an arithmetic sequence has a common difference, in this case, -4. And I could write an equation, an apparent formula, for the arithmetic sequence using a sub 1 and the common difference. And then from there, we turn sequences into functions. Remember, a sequence is a function whose domain, whose input, are the natural numbers. And so I can rewrite a sequence as a table, and more specifically a sequential table, meaning the x values increase by 1 each time as the y values represent the terms of the sequence. And what I did with an arithmetic sequence, I could do with one of these tables, meaning I could verify that it was linear by finding that common difference and write an equation for it in terms of x and y. Then later in the year, we talked about a special subset of the linear family, the direct variations, meaning graphically we were talking about the lines that go through the origin. And with the direct variation, we weren't limited to having tables that counted sequentially. We can have tables that jumped around on the x, like from 1 to 5 to 7. And because in a direct variation, and only a direct variation, y over x is constant, what I could do was I could test the y over x ratios. So -2 over 1, -10 over 5, -14 over 7. They all equaled -2, so I could verify that this indeed was a direct variation and write an equation for it. So what I want to be able to do now is take any table and determine if it's linear. I don't want to be limited to only knowing if sequential tables are linear. I want to know if any table, no matter how the x changes, can I determine if that data is linear.